Hello everyone. Today I am reviewing this paper which is titled Reducing the Dimensionality of Data with Neural Networks. This particular paper came out in the year 2006 and it has a lot of citations. The reason I have decided this paper is because uh, this paper, I believe, reintroduced autoencoders to the world. So previously, I think what was the history of autoencoders was that in the 1980s, uh, there were a lot of papers which had come about the use of autoencoders. However, the problem with this architecture was that this was never been successfully applied to a deep network, essentially network which consists of multiple layers. And the primary reason why the architecture of autoencoders failed for larger networks could be the training of the network itself. For example, people found that if you initialize the network with weights of less value, the gradients used to vanish to zero, etc. So it was extremely difficult to train the network as such, and people hypothesized that maybe in the future, where computational powers increase, maybe the usage of autoencoders would be more relevant. And now, in this year of 2006, when this particular paper was released, I believe this paper again showed the world how can autoencoders be applied very successfully in deeper networks and can be used for real practical tasks. And this change was really vital. Why are autoencoders important? It's because uh, let's say we want our AI to read from large pieces of document. Let's say this is a document, and we want our AI model to go through the document and identify the number of words or classify them into bag of words or BOW. Uh, Now, a single document might have thousands of words, and if you want to retrieve a query from a bunch of documents, instead of matching that query with all the documents separately, it will take a lot of time. So instead of that, what you do is that you take this document and you convert that into a lower order representation. So basically, what that means is that taking this document and then convert it into a vector of, let's say, 20 digits. That's it. Now you are representing this whole document by a vector of 20 digits, which is called as encoding this document, or it is also called code. This is called code sometimes in literature. Of course, when you are encoding this into a small packet, you are bound to lose some information. Now, the objective that which people have here is that the encoding should be such that when you decode it later, you should be able to retain as much as the original document as possible. So the training is being done from the original document being compared with the final document. So this is absolutely key because you have to be able to encode the document into a lower order representation or a smaller representation for it to make sense to match a query with a bunch of documents. Now, yes, you might argue that PCA or principal component analysis does exactly that, which is true. However, PCA always learns uh, to identify linear curves. It never gets to identifying non-linear functions. So, in a way, if you can do this PCA with neural networks, which is often what autoencoders does, you can present a generalized encoder in a way. So any function, any set of points can be represented in a lower order dimension using these networks. Just to give an idea of how exactly PCA works, what happens is that let's say you have let's say you have this bunch of points, right? Let's say, let me increase this dimension even more. Let's say you have these bunch of points. Now, I am using two coordinates to represent these points. I am representing them by x and I am representing them by y. So essentially, for every point, I am needing two pieces of data. Now, if you look at it closely, this particular set of points, there is maximum variation in this direction, whereas in this direction, there is minimal variation. So, if you are able to represent these points by their components along this vector, let's call it x hat. This is x hat and this is y hat. So by components, what you do is that you drop an orthogonal from this point and then you take the component like this, and then that becomes your data. That's it. So you're bound to lose this information, the perpendicular information, but I am willing to lose that information because the maximum variation is there along x hat, not along y hat. So ideally you choose this direction so that the squared error of this other orthogonal direction is minimized. Ideally it should be as close to zero as possible. So what you are essentially doing is that from two dimensions here you went to one dimension successfully. This is what PCA does. Now you can see that this is basically learning a linear representation because it's a linear line. In reality, the functions or the spaces can be non-linear, they can be more complicated, and that's why a deeper network which an autoencoder provides might be more generalizable. So in this paper we are trying to look at how autoencoders, or this paper kind of revived the field from 1980s and found out a new way of training the model itself. So I think the novelty of this model lies in the initialization of the weights, which they called a pre-training. And then after these weights are pre-trained, after that it significantly facilitates uh, the development of the model itself. So with this introduction, let us try to read the paper in detail. So let's start with the introduction. So they say that dimensionality reduction facilitates the classification, visualization, communication, and the storage of high dimensional data. And PCA is a widely used method for reducing the dimensionality. One of the main reasons is that we find the directions of greatest variance in the data set, and we represent each data point by its coordinates along each of these directions. Uh, now, they have mentioned that we describe a non-linear generalization of PCA that uses an adaptive multi-layer encoder network, which transforms the higher dimensional data into a low dimensional code, and then a similar decoder network which recovers the data from the code. Now, this was as such pretty standard, it was nothing new. Starting with random weights in the two networks, they can be trained together by minimizing the discrepancy between the original data and the reconstruction. The required gradients are easily obtained by using the chain rule to backpropagate error derivatives first through the decoder network and through the encoder network. So this kind of makes sense. Generally, how the autoencoder works is that, let's say this is the input, and then you pass it through autoencoder, you pass it through an encoder, and then you pass it through a decoder, and then basically you reconstruct the original input, and then the back propagation proceeds in this manner. First you back propagate through the decoder, then through the encoder, which is exactly what they have mentioned in this paragraph. So this is all right. Now we go to the novelty aspect of the paper. They say that it is difficult to optimize the weights in non-linear encoders that have multiple hidden layers. If you consider large initial weights, autoencoders typically find poor local minima, and with small initial weights, the gradients in the early layers are tiny, making it infeasible to train autoencoders with many hidden layers. And if the initial weights are close to the good solution, yes, then gradient descent works well. But finding such initial weights which are closer to the original solution requires a different type of algorithm. So this is what they are trying to do in this paper. They are trying to initialize the weights so that they are closer to the actual solution itself, and they call this as the pre-training procedure for binary data, and then they generalize it to real value data and show that it works very well. Now, we are not going to focus too much on restricted Boltzmann machine. For the understanding of the paper, it is perfectly fine if you just note in mind that this is sort of an unsupervised learning here. What you are doing is that you are taking two different layers at a time. So this is layer number one, and this is layer number two, and they are calling it as stochastic binary pixels are connected to stochastic feature detectors using symmetrically weighted connections. So let's say this is the stochastic binary layer and this is the stochastic feature detector, and there are weights associated with them. And then they have a weight update calculation through which the pre-training network learns to update its weights. So to understand this, you can just keep in mind that generally they have used uh, what they have done is that they have modeled the initial layers as binary vectors, which are modeled as a two-layer network called as a restricted Boltzmann machine, and they are doing this pre-training approach where they are learning the weights by considering only two layers at a time. That's it. After that, they are unrolling it and then they are learning the weights again. After the first time this pre-training architecture is unrolled, you get the encoder and the decoder where the initial weights are the same weights which the pre-training network has learned. Now the objective is that these initial weights would be a bit closer to the optimal solution, although that will not be the optimal solution. And then after that you run the standard encoder decoder process where you modify the weights through the back propagation algorithm. So we will devote a specific lecture to this restricted Boltzmann machine, where you will understand uh, how exactly they work, so that you will get a deeper understanding between of how um, this configuration can be represented as an energy function. Okay, so now let's go to the next part. After pre-training, let's try to understand what's happening. So after pre-training, what they are saying is that multiple layers of the feature detectors are pre-trained and the model is unfolded. After you unfold the model, the encoder and the decoder networks are exposed with the initial weights as the same. Now, in the global fine-tuning stage, uh, you use the back propagation method to fine-tune the weights for optimal reconstruction. That's it. So let's try to understand through some examples. So we are going to take basically two examples. Firstly, we'll take the example of these handwritten digits. So they have used a 784,500, 250, and 30 autoencoder. These are the different layers and these are the different neurons in each layer. So they have used this much size autoencoder to extract the codes for the handwritten digits, and the code layer simply contains 30 units. So essentially, each image was initially 28 by 28 over here. Each image is 28 by 28, and then you code it, and you have a 30 digit vector which you are using to represent this particular image. And what are the values of this? That is learned by optimizing this network by training to match this reconstructed input with the original input. Now, after the fine tuning on all the 60,000 training images, the autoencoder was tested on 10,000 new images. So, let's see what the outcome has been. So, in this image, if you can see over here, the first two are the results from the autoencoder, and the bottom two are the results from the PCA, I believe. So, what is the difference? So, these are the reconstructed images. Let's try to look at the 8 digits. If you look at this digit number 8, you can see that the reconstruction from the PCA is actually much better than the reconstruction. The reconstruction from the autoencoder is much better compared to the reconstruction from the PCA. In the PCA reconstruction, we can see that there are some lines which are removed from the digit completely, whereas uh, in the reconstruction by autoencoder, it appears that the digits have a lot of clarity. So even if you are coding the input into a set of 30 dimensional autoencoder, the reconstruction is much better as compared to PCA. Now they have considered a second example. Let's try to look at that. They have considered grayscale image patches, and the autoencoder clearly outperformed the PCA, they say. So this is the result from the autoencoder, the first one, and the second one is the reconstructed from the PCA. So you can see that the autoencoder over here clearly gives reconstructed images which are better than PCA. In PCA, everything appears a bit blur. However, here the reconstruction is much better. Now they have taken one more example, which is, I think, very interesting. What they do is that they train autoencoders on entire documents to allow fast retrieval. So the example which I had given before, retrieval of documents. Let's say you have a query and you want to retrieve the answer of the query from a particular document. If you are simply using a matching procedure, it's going to take a lot of time. What they have done is that they have represented these every single document in these 8 lakh newswire stories uh, as a vector of document specific probabilities of the 2000 most common word stems, and they have trained an autoencoder on that, and the number of code units that they are using for this is simply 10. So what's happening is that there is an initial layer where they are taking these 2000 most common word stems. So they are dividing this entire document into a bag of words. So let's say we take the this first line. Here we can see that every word is appearing once. So then you will assign the quantity 1 to every word. Similarly, you do the same process for an entire document. So you will get an array of a bag of words. So you can pick the 2000 most common words from the document. For example, if I wanted to pick a pick from these documents, maybe network would be there in the first common 2000 for sure. Now, this is where the power of autoencoders lies in. These 2000 most common words, 2000 most common words are represented by a series of just 10, 10 digits. That's all. It's unbelievable to for a human to recognize that a, a single document can be represented in such a lower dimensional space, and representing that is fine, but will it be able to reconstruct? That is what we are concerned about. Now, this is one method using autoencoders. At that time, the method of latent semantic analysis seemed to be very popular. I am personally not aware of this method, so I have made a note of this to understand what this method means. But this was a well-known document retrieval method which was based on PCA. And now both these methods they have compared, and so this is what the comparison looks like. So firstly, we can see that LSA with 50 dimensional representation still uh, is outperformed by the autoencoder with just 10 dimensional representation. So not only is the accuracy greater, but there is a 5 times increase in the computational time also, which is simply amazing. The same size LSA network actually performs very low compared to autoencoder. So autoencoders are clearly outperforming uh, the latent semantic analysis, which was widely popular at that time. Another example, what they have done is that if you look at this figure, so latent semantic analysis is based on PCA, and they are trying to plot the principal components of these documents in a single curve. So you can see that the green, red, purple, in general, there is some alignment. Whereas here, if you see in figure number C, these are the codes produced by the autoencoder. So here you can see there is a clear-cut differentiation. For example, all the documents which are related to energy markets are segregated along one line. All the documents related to interbank markets are segregated along the second line, etc. So the dimensions, the 10 different dimensions which the model is learning, and the way they are represented visually, they kind of make sense. So any document which lies somewhere here, you can be sure that it's related to accounts or earnings. Any document which lies over here, it's related to leading economic indicators. Here it's like a jumble. Even if a point lies here, I am a bit confused. Okay, it belongs to the red stream of dots, but there is also intersection with other curves as well. So not only is the accuracy better, the computational time better, but it looks like it is able to uh, understand the key parts of the document in also a much better way. So yeah, that's what they are seeing. The pre-training helps generalization because it ensures that most of the information in the weights comes from modeling the images, etc. The output from this paper which they have written is very interesting. What they have said is that it has been obvious since 1980s that back propagation through deep autoencoders would be effective for nonlinear dimensionality reduction, provided that computers were fast enough, data sets were big enough, initial weights were close enough to a good solution. Now all of these three parameters were satisfied by this paper, which is what makes this such a seminal paper. And the way I came across this paper is, again, I was looking at papers by Geoffrey Hinton, and this paper came across, and I was excited to know how the field of autoencoders has evolved, and this kind of revived the field after a gap of 3 decades, probably because the computational power started to increase with the as we keep on following the Moore's law. But interesting to know the journey which I have made two notes in my mind. Firstly, to make a lecture on this restricted Boltzmann machines, and also understand what is the meaning of latent semantic analysis in detail. So hope this paper helped you understand about autoencoders and how they were revived in the first half of uh, 2010, in the first decade. And also let me know, guys, which should be the next paper I should read. I'll be reading more papers as I come along, interesting articles, and cover all the seminal paper in this series. Eventually we are going to link all the papers that we are reading and kind of form a pattern historical analysis. But this is making us understand how the field of AI has evolved in a much better manner.